Okay, we're doing week 8, talking about PID process control. You're watching this because you downloaded the PowerPoint and clicked on the video link there. And once again, I take attendance. We've been taking attendance. Everybody's doing a pretty good job. There's new handouts that I gave out. The homework is just a little bit of PID general based on something you might find using the Google or the D2L reading. Give you the lab and the guide sheet. But in general, the PID is somewhat complicated. We're not going to dig into the math and everything like that very much. So the goal is just kind of a basic introduction. If you like PID and you end up in a job that has a lot of process control, you might get way into it. But we're not necessarily gonna do that here. Let's start with our week 7 review. That was our temperature measurement, and we did a couple things. We set up a PID controller, just a real basic one that you can get with a digital output controlling a solid state relay. Some of those that I had out there had also had a monitored contact, by the way, on those. We had the PID controller with an analog output. We'll talk about that one again a little bit. We didn't dig in that one very much. That's the Omega, but we will do that this lab, I think. All right. We use a temperature transmitter because it produces a linear input with analog input card, and then we used a thermocouple card for the nonlinear input. So that's kind of what we did, and it seemed to all go pretty well. You know, a little bit of hiccups here and there, but that's what you would get when you get into some of this temperature stuff. So first of all, we do need to reiterate linear versus nonlinear. So the thermocouples, I think we were using mostly K types. In the thermocouples that we had different ratings on them. Some of them said 0 to 900. We use, I think, on the scaling, negative 180 to 1370 C. But, you know, there's the thermocouple cable tables that I gave you. But if you look at those, you'll see that it's nonlinear response. So we need some type of signal conditioning. So the PI controller performed this task for us, and you know, it did pretty good. Those PID controllers are set up to be out of the box. You need something around the house or a little process controlled. You know, the cheap ones just work great. You know, they didn't need any compensation or anything like that. They did pretty good. Then we did using a temperature transmitter that did the processing, signal conditioning, and the ProSense ones, which are automation, you can give them automation direct, those did great. You know, we maybe put just a little bit of offset in there if you wanted to, but generally that was working great. But if we had the nonlinear process, nonlinear was the thermocouple card, and those were a little bit trickier because we didn't have any cold junction compensation on there, so our offsets seemed significant. You'd think, well, just what's the difference between room temperature and 0 degrees? Can we use that as an offset? Yeah, kind of, but those were giving us some weird numbers, and we'll talk about it. So the basic PID controller was that Rex 100. Got those on Amazon. They're pretty inexpensive. It basically controlled a solid state relay, so it was pulsing a solid state relay with pulse width modulation. We talked about the process variable. That's what you're measuring versus the set variable. And so the way the pulse width modulation worked is kind of showing you right here that it was the frequency of it. So it could keep it on, and then it'd be off for briefly, then it would be on again, and as it reached it, the time off would be greater than the set time on seemed to be the same, but the time off decreases, and that's what this is showing here. Is some modulation here, that as you start nearing the temperature that you want, the time off becomes greater. Now, the way that this pulse width modulation worked is like it had a couple of different modes. So it was on and off, on and off, on and off, rapidly or slower. Or if you were way off, it was just on. It would just turn it on. And so it just had just a couple of different modes. The pulse width modulation I'm showing here, it looks like each one of these is its own separate mode for, you know, time-based on and off. And really, that's not what we had. We kind of had zones like low heating or high heating when it was all the way on, medium heating where it was pulsing, you know, every second or every half second or something, and then near heat where it was maybe pulsing every 2 or 3 seconds, something like that. You know, different zones. You know, depending on your type of controller, you probably go in and set that up exactly. But these ones were real basic, and that's how they work. Like I said, the ones had an alarm contact that you could set an alarm for, and that would be on or off. That would not pulse. That would be like if you hit the temperature, and you could use that contact for PLC monitoring on this basic PID controller. And then it says complicated instructions. I guess, I mean, that's what you get when you buy these things. You know, they were translated from Chinese, I think, or some of them were in Chinese. And it was kind of hard to get through there. I think might have been a little bit impatient wanting to get it to set up the set point and see how it was going to put your bandwidth in there. And so, you know, the way that these work, you know, you can have a set point, and then you can have a dead band of plus or minus 2 degrees or plus or minus 4 degrees or plus or minus 1 degrees, versus are you setting a high limit and a low limit? You know, is your dead band being set with just the high limit and low limit to have it go back and forth? So when you're setting up a controller, you know, hopefully that makes sense. That there, you know, might be looking at it 2 different ways, where there's one, it just has a set point and then you give it the dead band, or the dead band is dictated by a high and a low. Okay. Maybe the Omega controller is more complex with additional features, but believe it or not, the instructions are kind of easier to read. The manual was much longer. This Rex one was only a couple page manual, and when you drill down into the, you know, everything, it was kind of a pain in the butt to get it. This one, the manual was like 20 pages, but it was actually easier to read and easier to go through. So once again, it can be a control with a digital output, and could use pulse width modulation, you know, with a solid state relay. That would be how our digital relay works. And then you can go in and, you know, set your set point and in your ranges and everything like that. But this also has control with a 0 to 10 VDC analog output, and that's where we were getting messed up. We didn't do this one because my bad, for what I was asking to do. We'll mess with it in the next lab. That people were setting it up, and it always had 10 VDC on the output. Well, yes, it had 10 VDC because you had a set point that was too low, or excuse me, too high, and it was reading like 75 degrees room temperature. Maybe you had 100 degree set point or something like that. And so it was trying to crank the heater at 10 VDC. It was trying to crank that output at maximum. But if you would have brought your set point in a little bit lower, you would have saw that, you know, and tried to heat this up, you would have saw that it would have varied that analog output to, you know, slow the heater down as you got closer and closer and closer. So that's what, you know, the way that this one would be working. It had a monitoring contact as well, digital, but it didn't necessarily have an analog monitoring contact. So we couldn't take this signal into the PLC, and that's where I had messed you guys up. We were trying to use the control signal for the analog output, you know, for the monitoring. Now what we could have done is, I guess we could have taken the analog output 0 to 10, and we could have put that into the input module, okay? And then as this was trying to perform its PID operation, and it was trying to control the fan or the heater or whatever, you know, 0, 1, 2, 3, 4, 5, whatever volts to get more cooling or more heating or less cooling or less heating, we could have monitored that with a PLC. And then I guess we could have had the PLC doing the analog control of the device. But, you know, a lot of these do stand by themselves, that they're made to control the device either digitally with pulse width modulation or produce an analog signal to control the controller, the heater controller, or the fan controller. we use a temperature transmitter, and this conditioned a nonlinear signal to be read by the linear analog card, and we set the card up for 0 to 20 milliamps, even though this was a 4 to 20 milliamp sensor. And we got really good results with this. This worked, minimal offset that you could have put in there some if you wanted to, but you used your scale with parameters that you had created in the prior lab. And this was a 4 to 20 milliamp sensor, and you set it proportional 0 to 300 degrees out. The one I've got showing right here is 0 to 500, so you'd use your scale with parameters, and you would set it to 0 to 500. Or, obviously, if this was a 0 to 10 volt sensor, you'd use your scale with parameters 0 to 10 and get your proportional control. But the temperature transmitter, really did work well for the analog card. Now, when we were using control analog input card, we did, you can put some offset in there, and we had a couple of students mess with the offset of just a little bit, because that transmitter was working well. But you remember when you thermocouples, we talked about cold junction, and what is the range of that thermocouple that you had set up. The ones I think that we'll be using next, they said they're 32 to 900 degrees Fahrenheit. That's potentially the range that would be ideal. But they, as we talked about in the analog lab, what if you're reading outside of that range, you're still going to get a signal. In generic K and J type thermocouples, there's charts for showing what the voltage is that you would want to be produced. So, getting all this equipment to match up and work and run, once you get it dialed in, it works well. And we'll keep talking about it, but what do you want? But we had the analog card, and there was different setups for the card that we had here for the analog card, and ours was a 6-input analog card. And it shows here that if you have this one's for a voltage analog input device, and it was external power that you could bring it in this way, or this one was external powered for a 4-wire transmitter. How you would bring this in. But what we had right here is we did have the 2-wire transmitter, and we had to run our own current loop. The transmitter was not externally powered, and it wasn't isolated. The power was not isolated from the signal. Our signal was part of the current loop, and so in this case, what we did is you have to jump the voltage and the current together. And so I like the way that we did this. We ran 3 wires out of this. We ran a banana lead out of the voltage, out of the current, and out of the return. And then if we want to run current, we just daisy chain those on top of each other as banana jacks. But if we want voltage, we just ignore the current, and then we can just go and use the voltage. And so this is something that we want to keep in mind for the next lab of what do we want to, what means do you want to use to measure the temperature. I'm going to let you pick. The thermocouple card used was a wiring diagram. Once again, you could look it up. We didn't use a cold junction offset, so we had to disable that, and you don't need a cold junction sensor and all this kind of stuff. But this is really nice. The thermocouple just gets wired into the channel, bang, and it's ready to go. You just got to be sure that you get it configured and kind of working like what you want to, right? This is a good one here. This is one of my favorites, Allen Bradley manuals. This is the ControlLogix analog I/O modules. They've got the digital ones as well, but this is a couple hundred pages, and it's just great. You can go in there and all the functionality of the IT6i, the IT6i2 compared to the IF6i or the IF8. How all these are just slightly different. And it's great reading. You could probably just spend the weekend reading this manual and just seeing how cool it was and how everything acts just a little bit differently depending on what you want. But this is one of my favorite manuals, and we had to dive into it and that's where, you know, it's got all these different wiring diagrams and functionality, and we are able to get it to go. So great manual there, digging into it. We're going to dig into PID a little bit more this week, but you know, the basic PID controllers that we had there, that are menu driven with those push buttons on the front, they're just an easy way to install and control a temperature dependent operation. And then a little or a lot of expertise can provide the desired result. You know, sometimes if you just know very little and you just need this to work, you can buy the cheap one on Amazon and, you know, push the buttons for an hour and figure out how it works, and bang, you're in business. Or if you're working for a company and you have heater controllers, these, you know, these are cool. They're just heater control units where you get these PID units. It's like a server rack where they slide in the server rack, controller after controller after controller, and each one is configurable and everything in the same manner that these are, with all the drill down menus and everything like that. But it's likely you probably need to know a little bit more about those and how to set them and how to get the burner control units working. So like I said, that was just kind of a little bit of an introduction to that. We're going to do a little bit more this week. Other temperature controls, we talked about RTD as another method of measuring temperature, and thermistor is another, talking about resistance, change of resistance or effect on current with your change in resistance. And all the three methods that we did, including the thermocouple, have pros and cons. All three methods can be utilized for process control depending, you know, on the question: what is the goal of the process, and what are your resources available? Do you need very high accuracy? Do you need very high range? Is it low range? Is it serviceable by the technician, or do you need the controls engineers to hack into the PLC? You know, there are just a lot of things going on here about what kind of control do you want and do you need, and then you're going to pick your process and your measurement to match that. And I'm sure that makes sense to you. And we're just doing a little introduction here. So this week we're going to explore the operation of the PID control user, and it's what we did. It's going to we're going to utilize the conditioned input signal to produce a desired output. The output can be digital like the prior lab. Okay, that's what we're going to stick with. It can be more exact if we want an analog output, and that is what that omega does. And what we'll probably do is I'll probably just have you have the PLC read that analog output. Okay, so we'll produce that analog output. Let's read it in and just verify that controller is working like we think it should be. We're not necessarily going to use that to control the process. We'll stick with digital output now, pulse width modulation, to get an idea of how that's going to work. Now, I did see these PID trainers I was telling you guys about, and it might be something cool for the future. And what this is right here is this little ball right here that floats up and down in this wind tunnel. And on the bottom here is a variable speed DC fan, right? So you can pick the speed up or slow the speed down. There's a sensor along here, and the analog proc sensor that tells you where you're at. And then at the top here, there's a damper, you know, that can open or close a little bit to let more air in and out. So what you do is you just get it all calibrated, and you set a height, like you want this to be 6 inches or 8 inches or 10 inches. You put that in the PLC and you hit start, and the fan comes on very high, depending on your PID, and the ball shoots up, and then it passes the 6-inch mark, and so the fan might slow down, and then the ball drops below the 6-inch, so the fan comes on kind of slow, and then it drops, and so it kind of oscillates back and forth, and then it lands on the 6-inch mark. And your PID can dictate, you know, how fast it gets to that, or maybe it takes a long time to get to there, but it hits it exactly perfectly, or maybe there's some oscillation or no oscillation. But you think of a heating and cooling process, you could turn on a heater to get the item warmed up, but if you overshoot it by too much, you might have to turn on a fan to cool it down a little bit, at which point it would cause the heater to come back on, which if you overshoot again might cause the fan to come on. And so you might go back and forth with a little bit, after a while, a little bit of heating and a little bit, just a little bit of cooling, and finally it hits. Okay, and so that this little PID trainer, maybe I got to get something for the future that might be kind of fun like this. Although if I get some 12-volt DC fans, I might try and get the ones that I built for you guys to work a little bit. But I just want to be sure you kind of get the idea of it. So the basics of the PID control. What is PID controller? It's a control loop, closed loop feedback control mechanism where you're taking the output and you're plugging it back into the input, and you're analyzing the difference between the output and input, adjusting your system, adjust the output, take the output, return it back to the input, and so it's a closed loop system, and it is designed to maintain the desired output by calculating and minimizing the error between what you're measuring and what the set point is. And the three components are proportional, integral, and derivative. This is where the math comes in that we're not going to totally break down into. I recommend, maybe the Google if you want to do all that you can, or if you want a special lab or something like that, you probably take a class at MSU that has really fancy PID trainers. But some of the things are just the same that we've already went over. The set point, that's the desired target value for the system. We'll be using temperature. The process variable is what the thermocouple is measuring. And the error is the difference between those two. And it uses this error to calculate the corrective output and applies it to the process. And we talked about using digital, looks like that's spelled wrong, or using analog. And we're going to be using digital. I'm going to try and set up a little bit of analog here for you guys. Let me see what I can find in stock. The terms work like this. The proportional term produces an output that's directly proportional. So that's what we've been talking about. Linear, and it's based on the current error value. So right away, if your preset value and the actual value that you're reading, if there's a difference, it is just going to subtract that difference, and it is going to produce an output that's just proportional to try and get it corrected. So if it's too cold, it's going to subtract the values, determine how much, and then it's going to turn the heater on, and it's just going to be a proportional response. If you're way off, then that's going to be all on. If you're a little bit off, if you're doing digital, it might pulse a little bit, and if you get close, it might pulse, very little, but it's going to be proportional. And the effect here is it leads to a faster response. So the proportional says you're off, you are going on, bang. But the thing is, it's going to get you there quickly, and so you might have a tendency to overshoot. Okay, then you got to shut everything off, and then you might even turn on cooling at that point. And then you would oscillate because you'd overshoot, and then you'd undershoot, then you'd overshoot, then you'd undershoot. And proportional control alone cannot eliminate all the error, okay, and will result in a steady state offset. So the first part of the lab, I'm going to have you generate a pulse width modulation add-on instruction. So you're just going to do pulse width modulation. And if you think about a pulse width modulation, it is just going to be a proportional response to the error between the two, okay? And so it'll be fun to see what you come up with that, and we'll go over it a little bit here. The integral term is based on the accumulation sum of the past error values, okay? And so what this is doing is it's taking a look at the past error, and remember, it gets updated, as the output gets adjusted, that gets fed back into the input because it's a closed loop, and then it looks at the error, adjusts, and that output then gets plugged back into the input, and so it repeats over and over, okay? And so the effect is it eliminates the steady state error offset that results from only using proportional control. So if you look at the past error, the past how much you've been oscillating or how much you overshoot like that, you can then make a prediction to how it's going to respond. But you still can have problems with the overshoot, and it would introduce some lag as well. Okay. Another problem with the integral is that because it's looking at past error and it accumulates the sum of the past, if it takes you a long time to reach your point, then the integral just gets loaded up. The accumulated sum gets large and large and large and large. And so by the time you get to steady state and you settle in to where the preset value and what you're reading are equal, you might have to still unload the integral value. It might just be full of garbage of accumulated error. And so that's a little bit of a problem that we'll take a look at and see if we can get our lab to work, to be, because our heating process is going to take a little while, and we load up our integral, we might have some issues there. And then the PID derivative term, this is trying to anticipate the future error by observing the current rate of change of the error. So obviously our error is going to be getting less. Hopefully our error is going to be getting less as we approach the set point, as we heat up to the set point. But if we overshoot the set point, then obviously the error is going to get large again. So it's going to be large, get smaller and smaller and smaller and smaller, and it's going to reach the point like, whoa, slow down, we want to go past it, and then all of a sudden we've got error again. So it's trying to anticipate this. It improves the system's ability by predicting future changes, reducing overshoot, and decreasing settling time. Now the thing is, if you change some of these, you'll find that it could really slow the process down. It might take forever then to reach the set point. Okay, and so that's something that you want to do is it could reduce overshoot, but it might be an hour before you reach your set point. No overshoot, but who wants to take an hour to get there? So between the two, that's kind of what the item or that it explained is, P says get me there now. That's the main one that you can kind of work with as your proportional gain. Here's the equation for it, and it's just the sum of them. You can see that P right here is just proportional. There's no square, nothing squared. It's just linear, just multiplied. Going to give you linear. Here's your integral right here, and then here is your derivative, the function of t over dt, changing time. So you can add those together. We're not going to get into all of this, but that's kind of what it's doing. It's adding those three to get the desired. So when you go and try and tune this, you can go in and on these little PID controllers or on the PLC, you can increase the gain on these manually to see kind of what it's doing. And proportional decreases the rise time. So you change your proportional, that's where you're going to get your bang for the buck. That thing is going to then move rapidly to where you want, okay? But if you go too rapidly, you're going to overshoot, okay? And you're going to have error. Whereas your integral eliminates that error that you're going to get, but you could also increase your overshoot, and then your settling time. It might take a while to get in there, okay? And then derivative could decrease your overshoot and reduce the settling time. So these are working against each other. This one is increasing your settle time. This one's decreasing it, but this one is definitely the one that's decreasing it. And so if you change this one a little bit, and then it's going to affect this one. So you change this one a little bit, it's going to affect this one and this one. So the effects of PID tuning is when you kind of go in and you put these numbers in and you try and adjust them to get the kind of response that you want, so it reaches it in the correct amount of time without having too much error or too much overshoot or stuff like that. In the lab, I have you do a little trend just to kind of mess with this, then we'll try and do it in real life with a heater. So PID controlled application. So we talked about temperature control, like furnaces, ovens, climate control systems. Obviously, you've got a furnace at your house where you want to keep things, your house temperature warm or cool, whatever. Motor control, maintain the speed of motors in robotics and industrial machinery, if you have variable speed motors. Vehicle systems, that's a big one that you got, is your cruise control is the good one. You know, when you hit cruise, it's got a little bit of a deadband where then it speeds up, and then when it reaches it, you know, you don't want to keep gunning the RPM, so you might overshoot a little bit, but then it backs down. And so that's a really good one, is your cruise control. And if you get into a really hilly situation, and you've probably tried your cruise control in the mountains, it doesn't work as well, because you know you kind of need self-tuning of all these PID variables, and it might be set up to cruise in a more moderate situation, not, you know, straight up and down a mountain, right? And then chemical process regulating flow rates, pressure, and chemical composition. I'm sure you can imagine that those applications of how you would want that the process to be under control. It says it's simple, robust, and effective, used in over 90% of industrial control loops. It's a reliable way to regulate systems without complex modeling. The modeling is actually complex, the math, but we're not going to dig into that much. We're just going to do tuning of it in its foundational concept in automation. That's why we're just taking a look at it in this lab. We can achieve more exact results. We talked about this. If the output is analog, we could change the speed of the fan, the cooling, amount of heat that's varied, increase the voltage to the furnace. If we used analog, but we're sticking with digital to get the response, and we're going to use that pulse width modulation to control an output. The first part of this is going to be just to create an add-on instruction with pulse width modulation. And we've talked about pulse width modulation, kind of shown right here, when we talked about variable frequency drives to generate to change the speed of an AC motor. That's how a variable frequency drive does. It pulses voltage for a longer or shorter amount of time to approximate, you know, the sine wave. And what we're going to be doing with this is we're going to be, you know, you're going to heat something with pulse width modulation, and when it's cold, you are going to keep the heater on longer, and then you'll pulse it off for a little bit, and then you're gonna keep it on longer, and then pulse it off for a little bit, and then you might get into medium heating range where you don't pulse it, where it doesn't stay on as long, and then when you almost get near the set temperature, then it's not going to be on very much at all. You know, it might just be pulsed to keep it at the temperature. Okay, and then this will be a little kind of a fun one. I think might have you think a little bit about how to do this and what it might look like. So it's just going to be switching rapidly between on and off state, or depending on which range you're in, high heating, medium heating, low heating, whatever, that on and off is going to be dictated by that for a set frequency, right? And when you, between the two of those, when you set, you're going to kind of get this variable pulse width that's going to produce more heating or less heating, you know, and you'll have to do a little math here to come up with what your duty cycle is going to be. And the lab lays out, you know, here saying a high duty cycle might be a 75% pulse, where a low might be 25% pulse, shorter duration. I think I've got you set up for 3. And so this is a Siemens add-on instruction, or Siemens function block. And so if you look at the Siemens one right here, it looks like they've got some scheduling going on here. It's likely your add-on instruction will just be unconditionally scheduled in there. You might lock it out if you reach a set point. There's different ways to do it, but you're probably just going to have an add-on instruction that's unconditionally scheduled. It's going to be taking in the temperature, your actual temperature, and it's going to be taking in the actual set point that you want, your set point, and then your sensor read. And then on the called the output side that's shown here, you'll be able to click up on the button here on your add-on, and you'll be able to enter, your heating ranges. What is your low heating range? What is your medium heating range? What is your high heating range? And it's going to say, hey, if it's more than 20 degrees difference, it's too cold, let's heat this thing up fast. And maybe when it gets within 10 degrees, you slow down. And then at 5 degrees, you slow down even more. Then at 1 degree, you slow down even more. And so when you put this block in here, similar to the Siemens over here on the right, you're going to see what your output parameters could be. Even though when you click the button here, you'll go and you'll set these items inside of your add-on instruction. And so you might want to use some of these parameters out here to create a bandwidth, for example, or you might want to create a lockout to stop the heater, because when you first do this pulse width modulation, and it gets close, it's cool, but then the thermocouple cools down right away as soon as the heater goes off, so it starts clicking on and off really fast. Click, 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 click. It's too much cycle time, and so I would get it working first and then figure out how to put in a deadband in there so that it's cycling between a preset range that you put on here. So it's I promised you, a long time ago, back in 260, that we would have this function block look here, and that's what this add-on instruction is going to look like, kind of this function block look to control the heating. And then the final part of the lab will incorporate a PID loop that will control the digital output controller by pulse width modulation. And so we're going to take a look at this. I don't know if this is probably going to change from what the lab is going to say. Let me take a look at it, because the heaters, this would work a lot better if we had an analog output. It would be cool to see, and I'll try and get some trainers set up for this or not, but otherwise we'll have the PLC do the pulse width modulation. There's a part of the lab where we put in a PID, and then we create a trend and take a look at it, and it's cool to see how it works. And the lab explains how that works. But if we can get this set up where we're going to use the difference between the control variable and the process variable, now the control variable is what's being calculated, right, can be used to determine the different cycle ranges of the PID output. We're gonna mess with it and see if we can get it to work a little bit. But it might. The issue here, is that we might get too much integral control, and it might just load up if it takes too long, and then it's not going to work like we want it to. We're going to try it. We'll see how we do with it, okay? Lab considerations. You can choose your temperature input method, whether you want to use thermocouple directly into the card or into the transmitter, or whatever. You figure out what you want to do. The output is a heat light lamp is what I've got. That's my furnace with a thermocouple mounted to it. The PLC can perform the PID operation, is what we're going to be working on, not the PID controller. And I'm going to look for some, I was looking 0 to 10 volt fans, so they're all 12 VDC fans. But I think a 12 VDC fan would probably work with our output card. So maybe a little bit extra credit here if I can do some more research and get some stuff working this weekend to maybe get an analog output to heat and cool this thing. So this lab, until I get, like I said, it'd be cool if I could get these trainers. These things right here, I'm like, oh, this is cool. It's like $2,000. I'm like, $2,000? I can make that for, like $10. So I just haven't got around to, getting all the pieces and parts. Part of it is just to see how the lab goes with you guys and what you're learning and seeing if you're enjoying it and getting the gist of it. And then we'll figure out what we're doing from there. Okay. So that was a quick hitter on PID, and the quiz is open, and I will see you guys soon.